to this place quickly. But it takes some time. Okay, it takes some time. If you are coming to the mean position after some time, then that is called heavy damping. It doesn't oscillate anymore. The graph looks like this. The graph looks like this. The amplitude decreases, but it takes a long time to come to the equilibrium position. Okay, so here what is the point? No more oscillation. Okay, that disturbance is over. No more oscillation, but energy is removed from the system. Okay, energy is removed from the system only after a long time, only after some time. Okay. Now, third one is what is desirable, which is called critical damping. Critical damping. In critical damping, which is most desired, there what happens? The amplitude decreases quickly. Okay, so this is the displacement versus time graph. So it had this much amplitude and amplitude decrease, or it does not oscillate anymore. This is not amplitude time graph. This is the displacement time graph. Okay, so the displacement. So that means if you are in the swing, you got it here. Okay, and if you want to stop immediately, someone holds you and brings nice and easy, and you are in the equilibrium position. There may be chance that you may oscillate, but little oscillation, but it is brought very quickly. So think about the car hitting the tree. If the car is fitted with the damping agents like shock absorber, that is the purpose of shock absorber in the car. If the car has shock absorbers, if the car is fitted with the very good shock absorbers, then what do these shock absorbers do? The energy which the car got due to the collision is quickly taken by the spring. The spring gets compressed. Okay, there is a spring in the car. So when the car gets a force, that force causes the spring of the suspension system, especially in bikes and all, you can see the spring, very strong spring, which can absorb a lot of energy. So if your car is hit with a very good suspension system, which has a very tight spring, that spring can absorb the energy from the car. So you will not notice that much disturbing jerk. You may notice only very little, which is not very unpleasant. Such one is called critical damping. So in critical damping, what are the main things? Number one, no more oscillation again, and the system or the object is brought to the mean position. Mean position means equilibrium position. That means the system has no energy in it. Is brought to equilibrium position quickly. What does that indicate? That indicates that energy is removed from the system quickly. Okay, so this is what is desired. Okay, this is what is decided. So this may be due to, okay, this is due to good suspension system or shock absorbers. Good suspension shock absorbers. Okay, and or some other damping agents or other damping agents. Now, even more desirable, you think about an ammeter. What is in an ammeter? What happens? You have a needle. If this is 0, assume that your reading is 3 ampere. Then the needle which was here, it quickly goes to this position. Now, if this ammeter has no damping, okay, then this needle will undergo lightly damping or under damp. As a result, how will the needle behave? The needle will make many oscillation before stops. Okay, the needle, it will go this side, it will go this side, again this side, again this side. So this decreasing of amplitude happens way after a long time only, which is very disturbing. You don't want to wait for the current to be shown after a long time you measure. But during that time, so many other changes could happen. So you want, if the needle is here, once you connect, you want the needle immediately to show this reading and to stop there. So we need critical damping. Okay, we need critical damping. Now, what is there in an ammeter to have critical damping? In an ammeter, actually there is a coil of wire which is wound around a metal frame, an aluminum metal frame. Okay, this is aluminum metal frame. There is a coil. It works by magnetic field, right? It works by magnetic field. So around that there is a coil of wire. This coil of wire is, okay, this is wire coil. Wire coil. This coil is wound around an aluminum frame. This aluminum frame has what? Has eddy currents. This aluminum frame can form eddy currents in it. Eddy currents means locally induced current, which will cause this damping. It causes damping. That means this needle will immediately come to the desired point. Okay, so all these things are called free oscillation with damping, without damping. Now, what is a forced oscillation? Any doubt so far? Any doubt?
No.
Okay, what is a forced oscillation? Forced oscillation is one in which you are giving some external force. Okay, there is some external force given to this one. Okay, so in addition, okay, so there is an external force. External force is applied in such a way that, now for example, if this is a pendulum, if it naturally oscillates, what will happen? It will undergo resistive force and finally it will stop. What if you don't want to stop this? You want the oscillation to continue as if there is no energy loss. You want the oscillations to continue. Okay, for that, what you can do is that when it is reaching here, you can give a force in this direction in the same way as this one. That means if you give an external force with the same frequency as the natural frequency. Okay, so if you give an external force, okay, that causes the amplitude to increase. That is called forced oscillation. Sometimes forced oscillation can cause the amplitude to increase, or sometimes if you are applying the force oscillation in the opposite direction. For example, if this was the one, and if the pendulum is here, if the pendulum is here, if the pendulum is here, for example, if the pendulum is here, you are giving a force against, then it will it will immediately come to stop. If you properly give at the correct point with the same, with the desired direction, it will maintain that. Okay. Now in the forced oscillation, what is important is resonance. What is resonance? What is resonance? Resonance is such that when an object undergoes oscillation, if you apply a force with the same frequency as its natural frequency, I told you every object has its own natural frequency with which it will have free vibration. So if you are giving an external force with the same frequency as that one, what do you mean by same frequency? When it is about to go in this direction, you have to give a force in this direction, right? So that means if you are at this point, if you are giving a force, you have to give a force in the direction of its motion, and that force should get repeated every interval right at the right time. So if the frequency, okay, if the applied frequency, this is the external frequency. If, sorry, when an object oscillates, when an object oscillates, when an object oscillates, if an external force is given with the same frequency, okay, with a frequency that is same as the natural frequency, okay, of the object, then what will happen? Then the amplitude will increase, okay, amplitude increases, okay, then the amplitude increases. This increase in the amplitude is called resonance, okay. This increase in the amplitude is called resonance. Okay, now, so remember, resonant happens. So if F naught is the natural frequency, if F naught is a natural frequency of the object, and if say, if Fr is the resonant frequency is the frequency of the applied one. Okay, if Fr is the resonant frequency or the frequency of the external force, frequency of the external force, okay, if both are same, then the amplitude will increase. If there are two sounds, okay, for example, for example, you might have heard that when certain opera singers sing, a wine glass breaks. Huh? Have you heard of that? When certain people sing, especially when girls sing with high-pitched voice, okay, this wine glass breaks. Can you tell me why? This means this glass has a natural frequency. This glass has a natural frequency of its vibration. Assume that its frequency is a 100 hertz. 100 hertz. This is the natural frequency. That means it makes 100 waves. It can vibrate 100 times in 1 second. That is its natural frequency. Now, when the singer sings, her sound also has a frequency, say F. If she adjusts her pitch of her sound such that she is able to sing, she is able to produce a sound wave with the same frequency as the natural frequency of this, then what happens? This will vibrate with increased amplitude. If this was its normal amplitude, this one causing an additional increase in the amplitude. Okay, it will begin to vibrate with this much extent, and this much extent this glass cannot withstand. Okay, the glass cannot support extending this much. That is why the wine glass breaks. You understand? The same. So this is resonance in certain cases has to be avoided. Certain cases is very desirable. For example, for music people and all, they may have a resonance. For music systems and all, music devices and all, they will adjust for resonance, like piano and all. When you hammer it, then that causes resonance of that particular note. That is why you hear a higher amplitude sound. But in other cases, resonance is not desirable. For example, if you have got very large bridges, and if certain vehicles pass through that with certain speed, this causes some frequency, some force on this one. If the frequency of the force from the vehicle is same as the natural frequency of this bridge, then the bridge will begin to have a higher amplitude vibration that causes breaking in this one. Okay, so these are some examples of resonance. Certain cases this is desired, certain cases this is unpleasant. Okay, that's all with oscillations. So we are done with unit 5, right? Now, have you done any unit 6 questions? In unit 6, it's mainly about uncertainty. When we do a past paper, I will teach you each and every portion. Now, what shall we do now? Okay, I'll send you a screenshot of this one.
Miss, I had a little bit problem with the parallax method.
Parallax?
Yes, miss.
Okay, in astronomy,
Yes.
Which is is it a question or you have got some concept problem?
No, miss, the concept.
What is that? You want me to explain it again?
Yes, miss.
Okay. 1 minute. Let me send it to you. Mashar, are you there? Mashar? You're there? Did you get the page that I sent you?
Repeat.
Second page, third page now is coming. This is the third page. Okay. Now others I'll send. Finished? Okay, so what is parallax method used for? What are the methods of finding distances to the celestial object? What are they? Okay, I will do this. Okay. um, okay, so what are the ways of finding the distances? What are the ways of finding distances of the celestial object? Hmm? Okay, so starting with the closest one. How do we find the distance to the closest one?
With Kepler's third law.
By Kepler's third law. And if it is little more further, okay, if it is little more further, how will we find out? Okay, that is what is Kepler's law? What is Kepler's third law? The time period. Time period is proportional to the cube root of distance to it. Okay, the time period is proportional to the cube root of distance, or t square is equal to k into r cube, or k into d cube, where d is the distance to that one. So you can find the time period easily, knowing the time period. And we also know that if the time period is in year, uh, and r is in astronomic, okay, then r is in astronomical unit, then k will be 1. So you will get the answer in astronomical unit, and you know how to convert astronomical unit to this one. Now, to find the distance to the nearest star from Earth, okay, how will you find the distance to the nearest star? For that, we use parallax method. Parallax method is used to find distance from Earth to the nearest star, near stars. Okay. So for that, what we do? Let this be sun. We are here. Okay. This is the Earth. This is the Earth. This is the Earth. Now, what we do? We observe the star. We observe the star, this closer star, at the background of distant stars. These distant stars appear not moving. They appear to be not moving, but we observe that these close stars appear to be moving. Okay, just like when we travel in a car, the nearby trees seem to be moving, but the farther trees do not move. Just like that, that is called a parallax effect. So now what we do, when we are here on Earth, we observe the star at certain time. Then we observe the same star 6 months later. 6 months later. Why do we do it 6 months later? Because that time we will be here. Okay, that time our Earth also will rotate. 6 months later, we know this distance. Okay, this 6 months later, we will be exactly at the same diametrical line with the sun at the center. And since we know this is one astronomical unit, this we know for sure. So knowing this, we can measure this angle. Okay, so this angle, this whole angle we can measure. Now, this angle is called a parallax angle or parallactic angle. And if you measure this angle, okay, so we can find this distance. Now, since it is closer distance, okay, so we know this one, we know this one, we have to measure this. What can we do? Sine theta, okay, or sine theta is equal to, or we can even use tan theta, because since this angle is too small, this distance, okay, since angle theta is very small, we can use small angle approximation. What is small angle approximation? If theta is small, theta is equal to sine theta, which is equal to tan theta. Okay, that means this distance, which we actually want, is almost equal to this one. All right. So here we can use tan theta. So if this distance is d and this is r, tan theta is equal to opposite by d. Okay, tan theta is equal to r by d, or therefore d is equal to r by tan theta. Okay, now if r is in astronomical unit, 1 AU, then tan theta will be the distance. So, okay, if theta is in parsec, if theta is in 1 parsec, then this will be, sorry, if theta is in arc second, if theta is 1 arc second, then this will be in parsec. All right. Okay, now what else? If this angle, if this angle is 1 arc second, then this distance will be 1 parsec. Okay, please memorize the conversion factor of this parsec and all. And because this will be 1 astronomical unit. Now, anything else? Mazherul, any other doubt? Have you started doing past papers? Okay, now what shall we do? Shall we do one unit 6 paper? Any other doubt you have?
No, miss.
No. Okay, so our syllabus of unit 5 is over. Now what you do is you start revising. Okay, you start revising. Now this you can use this revision schedule. Okay, when is your exam? It's in June, right? When is your exam?
Miss, yeah, unit 5 is in June.
Unit 5 is in June. Okay. 1 minute. Okay, unit 5 is in June. I mean, June, I think 15 or 16, right?
Yes, unit 5 and 6, June 7, June 15. 2 days.
Unit 5 is in unit 5. June, sorry. Unit 5 is on 7th June. And your unit 6 is on 15th June. So before that, we have got how many? We have got the whole of May left. April is almost over. One month time we have. So you should divide your time to have at least 2 rounds of revision. Okay, 2 rounds of revision. So in this April month, this is okay. So today is which day? Today is 23rd. So we have got 1 week left in this one. in April, okay, in April, you have to revise which chapter? You want to revise from the beginning or from the last of Unit 5? How many chapters we have in Unit 5? How many chapters we have in Unit 5? You have got thermodynamics. Then you have got nuclear physics.
Oscillation and astronomy.
Then you have got oscillations. Then you have got astrophysics. Okay, astrophysics.
Astrophysics, sorry.
Yeah, and then you have got Unit 6. So these two topics, can you revise? Or okay, fine, thermodynamics at least for the next, you've got 4 weeks. Now these two you must revise for the next week. Now we will have a Unit 5 lesson. Which day? Today is which day? And today is Saturday. Okay, today is Saturday, right? Yeah, today is Saturday. Now, when do you want to have your Unit 5 class? Next Saturday? Is this time okay for you?
Yes, miss.
Otherwise, no, not Saturday. Okay, I'll fix it. Okay, maybe Friday or Saturday. Friday is Friday 3 o'clock. Fine for you? 3 to 5 on Friday. If you want to have earlier, if you don't want to have this much late, then we can have it 3 to 5 earlier. You want that time? 3 to 5, inform me, okay? Either Friday or Saturday we'll have Unit 5 class. That time I want you to study this, plus I want you to do a Unit 6. I will send you one Unit 6 we will do together. I'll start with that today. Okay. Unit. Now, can you see the screen now?
So corner is blocked.
You got problem with this. Okay, this